So far, we have looked into how stresses in the soil are in the vertical direction only. So we have only the vertical stress so far. But of course, there's also horizontal stresses. So in this chapter, we are going to be looking at how the horizontal stresses work. Uh, so the vertical stresses work almost like fluid pressures in the soils. So you can consider depth times unit weight for the vertical direction. Horizontal stresses don't work like that. Uh, so for horizontal stresses, we are going to say it is a fraction of the vertical stress. So again, it is in that sense kind of like a fluid pressure, but uh, instead of being equal in all directions, horizontal stresses generally are less. In some rare cases, it can also be larger, but uh, so it is a multiple of or a fraction of the vertical stress. And uh, let's start from the 1D condition like we did for the vertical stresses. So if you are considering one-dimensional picture, but now we are considering the stress in the other dimension, that means, so let's call it, I don't want to call it 1D really, but that is what we have called it so far. So what I actually mean is in the horizontal direction, we have no strain. So we call that at rest condition. And in that condition, what we have is, in terms of effective stresses, so for that reason, this is also called K0 condition. So then your horizontal stress at rest condition, under at rest condition, is simply K0 times sigma vertical, where K0 is 1 minus sin phi. So it is related to the friction angle somehow. And times, if you have an overconsolidated soil, then you also have an additional term here, which is overconsolidation ratio. Let's remember, overconsolidation ratio is the maximum fast pressure over the current pressure. So if it is normally consolidated, this is 1 and it becomes irrelevant. But if you have applied a stress and therefore compressed the soil, the horizontal stresses get locked in there. So you get larger horizontal stresses for overconsolidated soils. And this exponent is usually around 0.5. So this is actually like square root of OCR. You can remember it like that. So as actually, yeah, it can be some different numbers as well, 0.4, 0.6, but it is approximately 0.5. So you can remember this as such. So Now let's also quickly write down here the straightforward bit. The pore pressures are equal in vertical and horizontal directions. So what that means is if you want to calculate the total stresses, then it would simply be K0 times sigma vertical plus U, for example. So the Terzaghi's effective stress works in all directions. Okay, so horizontal stresses are, as you see, very simple. This is it. But here we have limited this solution. This is the limitation. We have limited this solution into having horizontal strains to be zero. But what if they are not zero? What if you have some horizontal movement in the soil? Then things change. Now, let's consider, or let's make a plot like this. So this horizontal axis is going to be your horizontal strain, or actually if it is difficult for you to think in terms of horizontal strains, you can also think of let's have a wall here, like a retaining wall. And we are considering the stress state behind the wall. So what's going on here? So sigma vertical, sigma horizontal. So this is what we are considering, and air ratio. So let's say this is, to keep things simple, this is, let's say, a sand, and I'm going to declare here for this problem, K is sigma horizontal over sigma vertical. So if you do that, then I can write or wall movement here. It will be the same in compression. So here this side will be extension or tension. So if my wall moves to the right, I'm compressing this soil in the horizontal direction. Okay, so at zero strain or at zero deformation, if the wall doesn't move, if the wall is still in its original place, then what we are going to have here is we already defined as K0. Now, if I try to push the wall into the soil, or if I try to compress my soil here, what do you expect? You would expect I'm compressing this little element of soil from the sides, so I'm going to be increasing my stress. So let's say it goes like that. And similarly, if I move the wall away from the soil, I'm going to be relieving the soil of stress. I can't really apply tension to it because soils don't take tension. It doesn't work like that. But as you move the wall away from the soil, the sand will move, it will flow, and it will be able to still apply some stress. But you are relieving stress, so it goes down from there in the extension direction as well. But what happens afterwards? Now, I just said we are moving the wall so the soil is able to flow, or we are moving the wall into the soil and we are compressing the soil. So these don't sound like they are reasonable amount of deformations. These sound like we are failing the soil. So actually, let's consider it from that light. Now, let me plot a more Coulomb plane, and here is my, let's say here is the more Coulomb strength envelope, so here is my friction angle. And initially, what I have is, let's say this. So we said K0 is generally less than 1, because this is 1 minus sin phi. So let's say we are starting with a more circle like this. So here is my vertical strain, and here is my horizontal strain at the K0 condition. So we are starting from this stress state. Now, in the first case, what is going to happen is I will be, or actually let's solve the extension part first, it's easier. So when I apply extension to this soil element, or I'm moving this wall away from the soil, I'm reducing stress. Now let's look at how much I can reduce the stress there. Now if I reduce the stress, it will get, but remember the sigma vertical is still weight of everything above, or weight of everything above minus pore pressure. So the vertical stress remains the same, and I get kind of like a stress path with 45-degree angle in this direction. And then eventually at some point I'm going to hit the strength envelope. Then I'm going to be failing the soil, and no matter how much I continue to move the wall away, I cannot reduce the horizontal stress any further. Now in that state, so it will be, after some elastic deformation, it will be like yielding. And no matter how much I continue to move, it doesn't reduce anymore. So this I'm going to call Ka. Why am I calling it with a subscript A? Because remember, when we were talking about shear strength, we said if at failure your major principal stress is in the vertical direction and your minor principal stress is in the horizontal direction, then this is what you get. And this is called active failure. And then you get 45 plus phi over 2 angled failure planes. And in the other direction, it was called passive mode of failure. And in that case, what happens is you are increasing the horizontal stress now. So again, starting from this point, it's going to go like this first, and then go up like this. Because I'm drawing by hand, these lines don't look exactly linear now, but they are supposed to be 45-degree lines. And then you come to a limiting value of Kp there, which denotes the passive failure, and then your failure planes are going to be 45 minus phi over 2. So actually, in case of a wall, what you are going to see in the active state would be failure planes like this. Here is 45 plus phi over 2 from horizontal. So this is your active state or active failure mode. And in the other direction, what you get is -45 phi over 2 as an angle. And here you get failure planes that are more inclined. So this is your passive mode of failure. So what happens in between here, how the stress varies in between, is beyond the scope of this course because it requires some more complex analysis. But what we are going to learn is these active and passive states. And very simply, from trigonometry, you can derive that Ka is 1 minus sin phi divided by 1 plus sin phi. And of course, if you are working with drained parameters, these are all drained. And if you consider based on like geometric similarity of shapes, what you are looking for is a circle and a tangent to it, and what is the ratio between the two ends of the circle, or two ends of the semicircle. So that for the active case and passive case is the same problem. Therefore, very simply, Ka and Kp are inverse of each other. So based on this, now I can calculate what my horizontal stresses are at failure due to horizontal straining, as well as at rest conditions. So, okay, that looks fine, except here I specified sand and I started with no cohesion. So what happens when I have cohesion? Let's consider that. Actually, the full equation then becomes this. If you have cohesion, and this is actually regardless of whether it is drained or undrained, so you can do this for any more Coulomb material. When you do this, what you are going to get is the following. Sigma horizontal active is then Ka sigma vertical minus 2c square root Ka is what you are going to get. So this is your general equation, and if you reverse, if you switch places, then what you are going to get is sigma horizontal passive is Kp sigma vertical plus 2c square root Kp. Now, as I said, this is like the general form, but then so actually it includes everything. So if you are looking at drained parameters or drained analysis, effective stress analysis, then you are supposed to use all the effective stress parameters, and then sigma HA prime. Yes, I'm actually going to have to write this for this same thing with just primes. Where Ka is 1 minus sin phi prime over 1 plus sin phi prime, and Kp is 1 over Ka as usual. Now, starting from this, if you go undrained or total stresses, so this is effective stress analysis. Actually, instead of just putting the symbol, let's do that. So if you are looking at total stress analysis, then what you should be using are zero friction angle. If you put zero friction angle into Ka, Kp, then Ka and Kp become 1. And then what you get simply is from this sigma HA is sigma vertical minus 2Cu. Sigma HP becomes sigma vertical plus 2Cu. I simply put 1 for all of the K values here and Cu for C. And actually that makes sense, because if you consider the total stress envelopes, and here is your Cu, and if I plot the same problem here, starting from, let's say, this sigma vertical, this will be your, oh, bad circle, no. This will be your active circle, and this will be your passive circle. So if you look carefully, Cu is the radius of the circle. So here sigma HA is sigma vertical minus 2 times the radius, and sigma HP is sigma vertical plus 2 times the radius. So the good thing to remember here is the active and passive conditions. These conditions, the very end conditions of this plot, are the extremes. They are the failure states: active failure mode, passive failure mode. So the more circles there will always be tangent to your strength envelope. So they are always in active and passive conditions, they are always going to be tangent to your strength envelope. And now this this whole thing is called Rankine theory. Of lateral earth pressures. And that's it basically. And all we have left to do is to look at how it is applied. But actually, before going there, here you can have an issue if you look carefully. I have a minus in my equation. So under low vertical stress, you can have tension cracks. Now let me quickly rewrite here. Ka sigma vertical minus 2c prime square root Ka, or, so this is effective, or sigma horizontal active is sigma vertical minus 2cu. So this is total stress analysis, this is effective stress analysis. So I'm writing these together on the same page, but both of them won't be valid. Don't make that mistake. If you are dealing with effective stresses, this is valid. If you are calculating with total stresses, total stress version is valid. So they are, both of them aren't valid for the same problem. And how do we decide on that? You decide on it based on, you decide whether to use total stress analysis based on whether it is undrained mode. So if it is like a short-term change in stresses versus a long-term change in stresses. So if a slow change in stresses is happening, or if you are wondering what happens in the long term to your problem, you need to use the drained analysis. If you are looking at short-term changes, you need to use the undrained analysis. So anyway, we have a minus in the middle. That means if I have low vertical stress, so closer to the surface of your soil, you can easily have if calculations show this. So if you get a negative stress, a tension crack might develop. So again, if we think of this in terms of what happens if you have a wall, if you have a clay, and you are pulling this wall away from the clay somehow, or the wall is moving away from the clay, what you are going to have then is something like this. Because a certain height of that clay will be stable in itself, it will be able to hold itself vertically. So as you pull the wall away, that part ends up not moving, and then what you have is stresses acting on the rest on the wall, or if it's acting on the wall is acting the same thing on the soil. So here I'm going to say this very important advice. For these horizontal stress calculations for failure. What you have seen so far are the only equations you will ever need. So this is valid, and then of course this K0 definition is valid. So avoid all other equations, because you see these formulas in books, things like depth of tension crack. What is the depth of tension crack? And you see a formula for that. And then how much is the force acting on the wall due to soil pressure? You see a formula for that. Those will always make you take you to incorrect calculations. The reason for that is because they are always for very specific conditions, like no surface load, uniform soil, etc., etc. And those conditions very rarely come together. So how do you determine the depth of tension crack? Is the depth for which sigma horizontal active or sigma horizontal active, depending on, again, effective stress, total stress analysis, is equal to 0. So above that, you calculated less than 0, therefore the soils and wall separates. Below that, you have some stress, that's it. And similarly, you can define words like total active thrust, total passive resistance, because the passive stresses usually happen when, due to some other external force, you are pushing towards the soil, so the soil is resisting that. So resultant of now this time I'm not putting primes here, because total active thrust is always total, because that's what the name says. So even if you are doing effective stress analysis, it means you are going to be calculating the effective stresses and then add pore pressures onto them, therefore obtain the total stresses. So again, as I said, there are formulas for this in some books. Don't use them. If you use them, you will make mistakes.